The next thing that we need to add on to this is electronegativity and polarity. Remember, as you move across the periodic table, electronegativity increases the attraction for electrons. That's what electronegativity is. As you move across, it increases. As you move down, it decreases. Okay, so this is going to be important. We're going to look at why in just one second. So, when we are sharing electrons, if electrons are shared equally because they are being pulled equally by atoms, then the bond is going to be nonpolar. So if you look, for example, at hydrogens, those share the electrons equally because they have the same electronegativity. If two atoms that are sharing electrons have different electronegativity, so for example, hydrogen versus chlorine, chlorine has a higher electronegativity than hydrogen, and so chlorine's actually going to be hogging those electrons. So the way that we represent that hogging, let's look at an example for me to show you. So if I were to draw this HCl, okay, what I would do to show that chlorine is hogging those electrons is I'm going to draw an arrow. I'm going to show a vector. And that shows that those electrons are being pulled more towards chlorine than towards hydrogen. And so we are going to use this in order to be able to determine if a molecule is polar or nonpolar. Okay, so let's look at an example. So here, let's look at the nonpolar. If you notice, for CO2, oxygen is more electronegative than carbon. So you've got one arrow going towards one of the oxygens, another arrow going towards the other oxygen. Notice that those, what we call those dipoles, those arrows cancel each other out. That means that the molecule is nonpolar. If you look at CCl4, okay, you've got chlorines pulling those electrons, but notice you've got an up and then three downs. If you imagine that in a tug of war, those vectors, those dipoles, would cancel each other out. So it's going to be a nonpolar molecule. If you look at HCl, however, notice since Cl is more electronegative, the arrow is going to be pulling towards it. It's going to be pulling the electrons towards it. But notice there's nothing counteracting that. So since the dipoles do not cancel out, that means that the molecule is polar. For NH3, nitrogen is more electronegative, so the arrows are going to be going towards nitrogen. Notice that there's nothing, if you imagine like a tug or push of war, right? Those arrows are not going to be canceled out. That dot's going to move, which means that the dipoles do not cancel, which means that NH3 is also polar. And we'll talk about the significance of polar and nonpolar in the next lesson. Right now, I just need you to be able to draw these and determine if the molecule is polar or nonpolar. So let's look at this example. I'm going to draw my Lewis dot structure. Okay, so I've got HF, hydrofluoric acid. I'm going to draw the Lewis structure. There it is. Fluorine is more electronegative than hydrogen, so I'm going to have my vector facing towards fluorine because fluorine is hogging those electrons. Notice nothing cancels out that dipole. So as a result, HF is going to be a polar molecule, and that's it.